Okay, here for number 8, we've got two masses hanging from a spring scale like this. And the spring scale is going to read a certain number, maybe in kilograms, maybe in pounds or newtons, who knows. And this one reads in the kilograms, I guess. So we've got two 5-kilogram masses. The question is it going to read 5 kilograms or is it going to read 10? Let's take a quick poll. Put your thumb up if it's 5. Put your thumb down if it's 10. Okay, that's clearly a split class. So fortunately, we've got the equipment here to give it a try. So let's give this a try and see what we get. Yeah, come on up. And explain to us what you're doing here.
All right, well, we've got 2 weights here and a scale that reads in newtons. So if we put the first one on, about 2.5 newtons, roughly. And just for check, the second one on, pretty much identical. So, put the rope on one end, if I can do it. Got the rope on the other end.
For those of you watching the video, the tension in the room is you can cut it with a knife.
Tension.
Yeah, no pun intended.
And we'll turn it upside down, and sure enough, it's 2.5 newtons.
Okay, so the universe has answered this one for us. I guess if you bring a spring scale to the exam, you can give it a try yourself. The correct answer is it'll read 5 kilograms in this case. Any questions on that one before we go on? Okay, let's go ahead and go on to the next one. Okay, so here we've got a top view of a 5-kilogram mass starting at rest on a frictionless table. Thrusters are mounted to the mass so that they point as shown. The force that these thrusters exert changes with respect to time, and the magnitudes can be represented by this there. How far has this block moved after 10 seconds? So this problem kind of came with a free body diagram, except what is it missing? Yeah, it's missing an F net. So we've got an F1, we have an F2, that's going to equal F net, which looks like, at least at the instant that this free body diagram was drawn, it looks like this. That means as we turn this into equations, we're going to get F1. I might give that a minus F1, since to the left is often defined as minus, plus an F2 is going to equal, remember that F nets turn immediately into MA nets. This means that the acceleration is going to equal minus 100 minus 10t. Add 5t squared, subtract 10t, divided by m. The question is, how far does this block move after 10 seconds? We need to turn this acceleration into a position. How do we do that? Integrate. How many times? Twice. When we integrate this with respect to t on both sides, that gives us that a velocity as a function of time is going to equal, okay, watch my calculus as we go through, minus 100t, subtract 5t squared, add 5/3 t to the third, minus 5t squared. And if we're asked to find the position, we need to integrate one more time, again, with respect to dt on both sides. And that's going to give us that position as a function of time is going to equal 1 over m minus 50 t squared, subtract 5/3 t cubed, add 5 5/12 t to the 4th subtract 5/3 t to the 3rd. And we're evaluating from 0 to 10 seconds. And I'll go ahead and let you plug in the numbers. Does anyone have a number for this one?
I just had a question.
Oh, yeah.
Could you just plug in the numerical value for A instead of having to do that huge blob? You could just start integrating with that numerical value for acceleration.
Okay, so the question was, if you couldn't hear it on the microphone, is could we just take the equation for acceleration that we started out with up here at the top and just plug in time and evaluate that? No, we can't, because this is a changing acceleration. At t equals 10, the acceleration will be a certain number, but we can't just integrate that constant because this is a non-constant acceleration. So thank you for asking that. That's a very common test mistake. Any other questions, or does anyone have a number? If you wanted to, you could plug in your 5 kilograms before you started integrating if you wanted to. And it might cancel out some numbers. I don't remember exactly. Does anyone have a number? Okay, I got one person with an 833 meters. Do I hear a second? Okay, people watching this on YouTube, see if that's correct or not, and email us back. Okay, let's try number 10. Here we have 2 blocks sliding down an incline. Our goal is to find the tension in the rope. And let's go ahead and give it a try. First thing we always do whenever we solve a problem is we draw a picture. There is a picture here. Let's make use of it by drawing some forces on it. There's going to be a normal force on each mass. Now, because there's 2 normal forces and there's 2 masses, we need to make sure we label our normal forces. This is a plane with friction, so that means this guy is going to feel some kinetic friction going up, as well as some tension going down. There'll be a tension going up for the lower mass, as well as a friction going up. And both of them have weights. I think those are all the forces on the masses. At this point, it's always good to redraw a free body diagram. What we've drawn those force vectors on it, those aren't free body diagrams. You need to start with that dot if you want a real free body diagram. And we'll try to get all those forces in. I'm going to instantly turn my kinetic friction force into a mu n. And we're going to get something that looks like that. Is the free body diagram done yet? No, it definitely needs axes. Needs a theta. Looks like our theta is going to be right there. Notice I chose the axes that were parallel to the surface and perpendicular to the surface. We do need that F net. Our F net is going to be, we think, potentially pointing down the slope. It could be pointing up the slope. It could be slowing down as it goes down. And I'm going to turn the F net immediately into an M1 A net. Now, because this is a 2-body problem, we need a free body diagram for each and every body in the problem. So I probably should have labeled this free body diagram mass 1. And the next one would be mass 2. Its free body diagram looks a little different. in that in this one the tension's going up along with the friction. If you look at the friction back in mass 1, make sure you do put a subscript of 1 next to that normal, and this is normal 2. And again, those subscripts are important everywhere. F net also points down, but notice that this is M2A net. And don't forget the axes. And make sure you label them. Probably there should be axes on our F net as well. Okay, so we have, let's go back. Remember how we always solve problems is, number 1, we draw a picture. Number 2, we do our free body diagrams, in this case because there's 2 of them. And step 3, we finally get to derive equations. And one of the things we've been doing in class is we've been setting up tables of forces. It slows us down a little bit, but it does help us make sure we get the right answer. We have parallel and perpendicular forces. In the perpendicular, we got an N1 and a minus M1G. The adjacent part of M1G is in the perpendicular direction. So that means it's going to be a M1G adjacent would be cosine theta, which means that it is a M1G sine theta in the parallel and also negative. We have a let's make this way positive, which would make this one a minus mu k n1. And then we have a tension also in the positive direction. And all these have to add up to M1 A net in the parallel and 0 in the perpendicular. Remember, the universe doesn't care where you define your axes, but usually you want your axes to be such that the F net lines up on one of them. In most cases, that'll make your algebra easier. Yeah, quick question.
Why is friction perpendicular not parallel?
Well, that would be a really good question that I'm glad you asked. The friction is not in the perpendicular, but it is in the parallel. Thanks. Okay, but we have not one body, but we have 2 bodies, so we have to do another one. Again, to maximize your partial credit, you should always label these. That first table is for mass 1. This one's for mass 2. And we defined uphill as negative, I believe, in the previous one. So we're going to have a negative mu k n2, a negative tension. These, of course, should be in the parallel direction as the audience is waving their hands trying to tell me. And we also have some M2G sine theta and a minus M2G cosine theta in both dimensions. And we have an plus N2 in the perpendicular. And when we add these up, we get m2a net and 0. And as I look around, is anyone dissenting strongly? Okay. Then we can go a bit further. We can try to turn these into equations. One of the things we can see about this chapter of Newton's third law is that it makes for problems that are reasonably long, because there's a lot going on in them. So I'm turning the tables we made into equations. And we will end up with 4 equations. There's a reasonably good chance that there'll be 4 unknowns. And as we look at this, the things that were given to us were the mass. We assume we're on Earth. We were given theta? Yes, we were given theta. And we were given all the coefficients of friction. And as we go through this, we see that the thing we're looking for, acceleration, can be found in, let's number these equations, 1, 2, 2, 3, and 4. If we take N2 and plug it into there, and tension and plug it in there after we have taken the normal force and plugged it in there, we could then solve for the acceleration. Now, if this were a test, what might you write at this point? Right. 4 equations and 4 unknowns implies that we can solve. And then you'd go into the next problem because you'd get 9 out of 10 points at this point. Yes?
We're actually looking for tension, not.
Oh.
So you want to sub A into A net, right?
Sorry. It sounds like we're looking for tension. It's algebra. Yeah. Let's go and leave it there. Maybe I'll put up a solution after we all go home because we need to get out of here in a few minutes. Okay, finally, number 11. A future space station can create artificial gravity by rotating. In a sketch, clearly show me where in this space station you would be able to stand normally in artificial gravity. I'm going to draw one of the rings of the space station exactly face off so we can look at it. And the space station is going to be rotating in a certain direction. And let's say that you were a person that happened to be standing on the outside. First of all, what forces are acting upon this person? Yeah, none. There's no weight. There's no gravity out here, so you have no weight. You're weightless. So what would this person do if he or she were to be standing right there with nothing connecting them to the space station? Yeah, they'd fly away at that velocity because, an object in motion stays with no external forces acting on them, stays in that motion, in this case this velocity vector in a straight line, forever and ever and ever. So that's not a place where you want to stand. Meanwhile, let's pretend you were standing right here. Right there, if I were to draw a free body diagram on the person would want to be going in a straight line, but as they go in a straight line, they kind of crash into the ground. So from their point of view, what does the ground seem to be doing? Pushing up, so that an instant later, when the person is here, the velocity vector has now been pointed this direction. And when you're going that direction, you run into the ground again. The ground pushes you up, and you are now right here, going in this direction with a velocity. So if we were to look at this original person right here, the free body diagram would be nothing but a normal force pointing up, and that's going to equal mv squared over r because the person's going in a circle. So where do you stand normally? You stand with your feet on the inside of the outer part of the ring. Yeah, so our F net is mv squared over r because whenever we're going in a circle, the sum of the forces, which we call the centripetal force is the sum of all forces, equals mv squared over r. And the next question is, what rotational period will provide normal gravity? Well, if I take my free body diagram and turn it into an equation, we get this. In normal gravity, if I stand on a bathroom scale, the normal force of that bathroom scale is going to read my weight, which is mg. So that means that we get mg is going to equal mv squared over r. The masses cancel out, and that means that my rotational speed has to be equal to the square root of gr. Now, the question's asking us what rotational period will give this to us. Well, we remember that velocity is a change in distance with respect to time. In this case, we're going a circumference every period. That has to equal the square root of gr. And if we were asked to find the period, that would give us 2 pi r divided by the square root of gr. We could simplify just a little bit if we wanted to, and we could say that the period is 2 pi the square root of r over g. And at this point, you could check your units, make sure it makes sense, and then you could plug and chug numbers. We'll leave it right there. Thanks a lot for listening to this real quick solution set for last year's second exam. Thanks, everyone.